So this next talk is by Ron and Longsheng and Subrata, but he's not here.
Yeah,
but he worked on the talk as well. So yeah, Subrata did some work on the talk as well. So and last year at the OSFC, Ron talked about that this is about the RAM stage and how it's already possible to substitute the RAM stage with a Linux kernel, because the Linux kernel has so much stuff that the RAM stage does. So we don't really have to use the RAM stage. We can just substitute it and have all that work be in the Linux kernel. So and now this works with Coreboot, but now there's work done to make it work with the Slim bootloader. And so this is what the talk's going to be about. Please have a big round of applause for Ron and Longsheng.
Yeah, a minor correction. All the heavy lifting on this was done by Subrata and Sheng. I've just been kibitzing. And actually, the slides are kind of really Subrata's, but he couldn't make it and asked me to stand in for him. I changed the title a little because that's what you get to do when you give a talk for someone. So it doesn't say Coreboot Lite anymore because it's my favorite word. But anyway, on we go. So we've been working on this maybe since last year when I first brought up this idea at the talk, and so we just wanted to talk about where we are. And Sheng is here to watch over me and make sure I don't get too far off track. But we were going to talk about Rampayload and Linuxboot. And my original interest in removing the RAM stage is around Linuxboot, but he's also worked on the Rampayload for non-Linux kernel applications. And the idea is you like to try and remove as much redundancy in the RAM stage that is replicated in your payload as you can. So here's a quick status on that work. So the observation was that there is functionality duplication in a boot flow, and that can actually impact firmware boot time. Now, for most firmware, we really don't care because most firmware burns minutes like they're going out of style. But for, of course, Coreboot, every 10 milliseconds or so you add is the 10 milliseconds that you've made your boot time worse. So if you can possibly remove that kind of thing, you can get rid of it. And so basically what this talk about is really from the Coreboot perspective, you don't see a RAM stage in there because it's either been removed or functionality got moved into PostGar. So that's the goal here. And so this is a summary of the work Subrata has done on the latest IA Chrome platform. And I was there kind of providing the Linux kernel and the uroot image for him and then testing what he was doing. So here's your classic Coreboot boot flow, which probably everybody in here knows by now. There's your boot block, your ROM stage, the PostGar where you tear down caches RAM and do some NTRR stuff, and then RAM stage. And this is a heavily FSP-centric slide, as you can see. This is not like, your grandfather's Coreboot, because there's just a lot of binary blob action in here with the FSP. But that's kind of how it's done on newer Chromebooks today and other platforms. And here's some rough size numbers. You can kind of see at the right, the RAM stage is a 1/4 meg. And then we run depth charge. So my interest in all this is not actually in depth charge, it's in Linuxboot, but this is what the flow looks like on a Chrome platform. And the experiment he did was to yank out the RAM stage. And even though, and here's where things get a little concerning for me, because he did yank out the RAM stage and what did make it work, that's great. But notice what happened here for depth charge purposes. And I'm the guy who made these red, they were black. But there's a little bit of PCI stuff going on here. And yeah, there's ACPI table creation going here. And that was a little concerning to me, although he did get some kind of nice numbers. He reduced the overall image by 150K. And again, in a kind of an FSP UEFI world, that's just peanuts because those things chew up megabytes like nobody's business. But still, from a Coreboot perspective, that's a pretty good size reduction. And but the thing I like is chopping off 240 milliseconds, because again, on a Chromebook and on IoT things, every 10 milliseconds you save matters. I was telling Sheng a story last night about a visit I had from the Navy one year. These are the guys who put the sonar in the subs, and they said you don't like to really have a sonar that takes a long time to boot because then you could be dead. So real life application, I've heard, from DoD in several cases where boot time is incredibly critical to living. And so, 240 milliseconds is no small gain in boot time performance. Subrata makes an interesting argument. He reduced the code size 41%, and in some notional measurement, that's a 10% reduction in bugs, which is not something I ever thought of as kind of a neat argument. And again, you can shrink your SPI flash footprint by a bit. This is kind of neat, but again, I'll say it again, the areas in red for me are a little concerning because my original thought on this is we go from postcard right to Linux and good things happen. I would like to mention, if you get a chance, look at UBMC. UBMC, to me, is the ultimate example of getting this right. There's about 1,000 lines of assembly code that turns on DRAM, then they load Linux to RAM and jump to Linux. So if you really want to look at a pretty cool example of no RAM stage, UBMC is a great place to start. Now, I'll further mention, this idea began for me years ago when I was experimenting with having Plan 9 replace the RAM stage and got some pretty reasonable results. That was talked about at the 2015 Coreboot meeting in Denver. So where this idea originated, at least in my mind, in 2015, I was doing a lot of work on RISC-V, and I kept looking at this RAM stage, which was basically a load the payload RAM stage, and thought, well, why do I even need that then? And so I did do some experiments, and I did determine that there were cases where I did not really need the RAM stage. Talked to Patrick Georgie about this, and he kind of had a neat idea, which is if we could get more flexibility in how the RAM stage is set up, simply by making it an optional where appropriate. And again, I'll go back to the earlier slide. Maybe it's not always appropriate to remove the RAM stage, but maybe when we want to have the option to do so. And a more interesting idea, which you're actually going to see realized in the Slim bootloader, componentized RAM stage. So we make the RAM stage a payload. We make that payload a lot more configurable than it is today with components you can add or remove. And, during the 3M Deb talk that Piotr did yesterday, which was an excellent talk about virtualization support in Coreboot, they had a little bit of a tussle there because they kind of wanted to add things to the RAM stage, but that's a headache because when you add things to RAM stage, you more or less have to upstream them to Coreboot, and it didn't seem really appropriate for some of those components to be upstream to Coreboot. So if we had the idea of a Rampayload where some pieces came from Coreboot proper and some pieces came from my special thing, that might be a lot more powerful than what we have today in Coreboot. So that's another thought. I know for a fact, because we've done it, that Linuxboot would be a little better if we could basically ditch most of the RAM stage altogether. And the areas in red I pointed out, we have experimented with removing them. One mechanism is to actually include the ACP generation in a Linux init RAMFS, not in Coreboot. And that's actually a fairly practical thing to do. Trammell Hudson demonstrated it on a number of server platforms. So kind of the discussion, as you all know, got a tad heated on the review site and the mailing list because I feel like maybe to some extent there was a little bit of hole in the communication. PCI support. Should you remove PCI support? Should you remove the RAM stage and then add PCI support into postcar? That to me doesn't make a ton of sense, right? It's not really about moving the deck chairs around. It's sort of like saying, I can remove the RAM stage because my payload does everything that the RAM stage is doing. And in the case of Linux, that's true. Linux can configure a PCI bus nowadays where 20 years ago it could not. But if we need a bunch of things for depth charge, it might make sense just to keep the RAM stage and not do all this. But maybe we should make it componentized. Maybe that's the right model. If it sounds like I'm asking more questions about how Coreboot should do this than giving you answers, that's what I'm trying to do here, right? I'm trying to spur a little discussion and thought about where should we be heading with the RAM stage. Now, Patrick Georgie put up a Rampayload CL for discussion, just a document, later abandon it. I'm probably going to revive it and try and resume the discussion again, and hopefully we can come to some thoughts on that. One of the things that tends to come up a lot is S3 support, critical for mobile, except Surface doesn't use S3 at all. So S3 isn't really an issue for Surface at all. They use something called Modern Standby. They've modified all the drivers so that they do the right things for power. Maybe we should be looking at things like that instead of sort of clinging to S3 and other things like SMM. Servers don't care about this stuff, right? So, I mean, I've never talked to anyone who said, I really care about this in my server. So I'm happy to shed some of the things the RAM stage does today on a server. And then Sheng reminded me that IoT doesn't need any of this either. You turn on the IoT, it runs hot the whole time because it's doing stuff like the sonar in your nuclear sub, for those of you who have a nuclear sub. So, not really an issue. What we've decided to do until we can better refine what we think ought to happen in Coreboot, we're going to take a little pause on this Coreboot work that I described here. I'm going to try and revive the discussion in a document, and we're going to see about bringing people into this whole discussion of what do we do with the RAM stage. Finally, I did talk to one person about hardware, and I didn't remember the conversation well enough to put it down here, but basically there was a case where the RAM stage configured PCI, and it actually caused trouble for the payload and the payload's access to the PCI and configuration of it. So it isn't just about time and space. It can actually be about correctness. So the RAM stage can do things that cause correctness problems for the payload. So I think that the time is coming when we've really got to think about the configuration and where we go with the RAM stage now that we have more capable payloads than we used to. And we might not only do redundant work and take up space in flash that we don't need to, we might actually conflict in things we do in the RAM stage with things we want to do in the payload. This actually led to one thing in Coreboot. We had been calling it the RAM payload in Coreboot. We decided to change the name to payloader to make it clear that that intermediate function after the RAM is set up and before the payload is just the thing that loads the payloader. And there might be something else that does what the RAM stage does today, or there might not. It might be just a Linux kernel. Certainly on the RISC-V, it's just going to be a Linux kernel. Probably on ARM, it'll just be a Linux kernel. If we ever find an open x86 where we can own it from the ground up the way we used to, probably would just be a Linux kernel. And so that's it for the Coreboot part of this talk. These are really describing Subrata's work and then discussions we've had in the reviews and with Subrata and I. And that's kind of all. And now I'm going to hand off to Sheng, who's going to talk about the Slim bootloader work.
Thank you. Okay, thanks, Ron. So now I'm going to talk about the Linuxboot POC on Slim bootloader, what we have done so far. So as mentioned by Ron yesterday, so the key essence here you can see is let Linux do it. I think we are on the same page where that the firmware has to done very minimal work and then hand off the majority work to the kernel itself. So that's why you can see on the photo on the right-hand side, that's all similar to UEFI, Coreboot RAM stage, U-boot SPL, or the reduced stage 2 or stage 1B, which is a Slim bootloader, which is what we're going to do. So all these three will boot directly to Linux kernel. So these are the concepts that we're going to bring today. And Linuxboot it has been deployed today and is going to be in a lot of servers. So that's why it's gaining momentum now. So okay, let me go through the architecture design. So you can see the first one is the boot stage to Linux OS is the original design without the Linuxboot. So I'm sure those who are from Coreboot, you can familiar with this. These are the streamlined process, stage 1A, 1B, stage 2, and then the OS or the UEFI payload, and then boot to the Linux OS. But you can see when you go to if you combine with the Linuxboot itself, so you can directly from the stage 2 jump to the Linuxboot and to the Linux OS. And so what is new over here? The things that we can see that we have removed the need of payload to load the OS, where we can use a Linuxboot to do all the kernel initialization. And also the stage 2 is simplified as a Linuxboot kernel exchange. So let me go to the next slide, see how it's simplified. Okay, so you can see over here, these are the normal boot flow that we have today. I'm not going to go through everything now. So these are standard, right? So let's remove this. So with Linuxboot, we are able to remove a few things prior to this. there's no more, you can see no more payload. You can jump directly to the kernel entry point from the last one. Okay, so that's all right. So that's nothing much to see over here. But wait a second. How about we take out even more stuff from here? Well, we can also take out certain part of ACPI tables and then move it to kernel itself. MP init. We can also even take out MP init and let the kernel do the MP init itself. This will even save much more time. So the two key components here, as we can see, is that with all this thing has been removed, we can see faster boot time observed. For the QEMU, I think we look around 300 milliseconds, the boot time saved from the stage 2 itself. And then no more redundancy. What's the point of doing redundancy? To do PCI enumeration in the stage 2 and then you do it again in the kernel, that doesn't make sense at all. So that's why the goal of here is to remove the redundancy and the boot time. So these are two key points that we achieved so far. So okay, let's go to the next one. The build Linuxboot payload is quite straightforward. Thanks to Ron. You just git clone, go to the folder and make stuff, get stuff, and then that's all. You can do it yourself or you can get the kernel directly from me. Okay, so how to build it? How to build the Slim bootloader. My colleague later will tell you how to do exact porting, but this is a more simplified version. How to do it? So you just git clone from a Slim bootloader GitHub, and you just need to, how you build it is you just need to fill in these parameters. The first one, the CMD line, there's a dummy file, you don't care about it. But the one highlighted in red color, these two are the one you need to change. The first one is the Linuxboot image file name, you have to put it. And then the second one is the command line .exe, where the command you need to pass to when you're loading the kernel. Okay, so these two you have to store inside the payload package / payload bins. All right. Okay, so these are few parameters where you can change Pyro to using Linuxboot. This if you are from Coreboot, you know Coreboot, you can change the kconfig, right? So these are kind of similar. So inside the build loader Python file, there's a few parameters you need to change. You need to set enable Linuxboot equals to 1, which enable the Linuxboot support. And the second one, the reserve memory size is you need to increase the reserve memory for Linux kernel loading in case that your Linux kernel is bigger size. And then, as I mentioned just now, you can disable the PCI enumeration and also disable the MP init, but just directly set it equals to 0. You can try it yourself. It's pretty straightforward. It's already there. And also from that side, I highlighted in red because if a QEMU, you have to go to QEMU package folder. So there's one. The first one is the payload size itself. You change it according to your kernel size. And the second one is you have to add the payload ID to support Linuxboot. So that's all. Quite straightforward, right? So let's go to the demo. Okay, let's hope it works. Yeah. Okay, that's it. So these are demo I want to show you. It's pretty fast, but it's not fully optimized yet. I haven't optimized further because I've done it. Okay. Sorry? Oh, okay. Yeah. Currently, I'm actually using the UpSquare board as shown by my colleague just now. This is an UpSquare board, which is a community makers board, whereas you're using Intel Upper Lake silicon itself. And you can just use it and then hack it any way you want. So this is how we try it. From there, you can see it's pretty fast, but it's not yet optimized. It can further optimize further to make it boot even more faster. All right. So that's it. So here is a summary. So as we have showcased, the Slim bootloader has finally officially support Linuxboot itself, and it's because so it actually shows that Slim boot is a flexible boot solution where you can change it quite easy to optimize it accordingly. So the second thing, as Ron mentioned, Linux is the mainstream. It's going to be deployed in more and more servers itself, especially. So that's why we are making this effort to embrace open source or industry requirements. And the last, we are trying out on a Slim bootloader configure stage 2, where you can also try out yourself. So yeah, pretty much. Thank you.
Thank you, Shane. Let's have a round of applause. This
Q&A.
one. You have a lot of time for questions.
Okay.
A lot, like.
Yeah,
I won't do.
or you can all go out and get some more food.
I wanted to do an equation that you solve for x, but no.
Yeah. I did want to mention the shell prompt there that came up was from a shell written in Go, because that was the uroot userland in Linux. So all the code there is code written in Go. Yeah.
Yesterday there was a mention about Linux drivers not happy if the PCI enumeration was not done by the BIOS.
That was 1999. That was true.
So
So that was kernel. Believe it or not, I believe that kernel was 2.0.36. So
there is no such restriction these days.
there actually is. So the restriction is people are always happy to produce code that depends on the BIOS having been run. And on the Winterfell nodes from Facebook, we did about 2 years ago find an AHCI bug because we weren't doing a thing. And Jean-Marie Verdun pushed a patch upstream to fix that. So this is why, and I don't think I brought this out as well as I should have yesterday. I was saying it'd be nice if we could find a way to make it a policy for Linux to be booted on these machines without all these Dixies having been run, because you do. It's the only real way to find a buggy driver. But that was in 2.5 years. That's actually the only bug I can remember hitting with that kind of problem.
So do I understand right, if the Linux payload will be able to handle the PCI enumeration before transferring to the actual Linux kernel?
Yeah.
Okay.
Yeah, we've been doing that for a couple of years now.
Thanks.
Yeah. Sorry, I wasn't a little more clear.
Hi, Ron. I think Linuxboot is really a great idea. So here, since we are trying to do more things in kernel, right? So basically, we have to draw a line between the firmware and the kernel. They should have a boundary. Right now, since we are moving more things from firmware traditional BIOS side to the kernel, and it might make kernel a little bit board specific if we do more things. So how do you see how do we keep the balance between these two? What basically saying, if board specific, we leave it out and then do not necessarily do it in kernel. So basically, they have some balance you have to consider, right? So
we've been doing that a lot, and actually one of the nastier board specific things has been GPIOs. How do you get that stuff to communicate to the kernel about things like GPIOs? And Coreboot, we're using the flattened device tree.
Okay.
I actually was watching a Slimboot talk, and I was screaming inside my head, flattened device tree, flattened device tree. And I kind of wish that you all would be looking at that, because it's solved the problem now for a long time, and why not just use it? And other than that, I have no idea. I don't have a general answer to your question. It's a really hard problem.
Okay.
Yeah.
Okay. That's great to know that trend. I think.
Yeah.
It's really.
Yeah, it's actually, the funny thing is it's an area we went over in a lot of depth 20 years ago, and that's the origin of the Coreboot tables, actually, right? We were communicating information from Coreboot to the kernel, and in a lot of ways we lost 20 years while we went into this proprietary jog we've been on, and now we're back trying to solve the problem again. And I'm hoping this time around we stay on the open path and get this thing solved right. So
Okay.
that's
Okay,
my
thank
hope.
you, Ron.
Yeah.
So I noticed in the Coreboot talk yesterday, it looks like you have the separate stage to load the payload after the RAM init stage. Right?
Yeah.
The payloader.
Yeah.
But in your Coreboot work, I think you're trying to load the payload directly from the ROM stage. So
Yeah.
which of the two approaches is the right one?
I don't know. This is still all up in the air, and I think the main reason we named it payloader was to avoid any implication that we were going to recreate the RAM stage. I think that the right mode is if you can get by without the RAM stage, do so, because you save time and space. But at the same time, that was a conjecture from last fall, and I think that if you look at the work with depth charge, there's a clear need for a RAM stage there, and so, or there's a clear need for something right now. Thing that we didn't mention yesterday about Coreboot is the format for all the things is going to be self. We were essentially dropping the stage format entirely, because one way to look at a payload as a stage, if a self thing has one segment and it's already at the location that it's at, it's kind of implicitly a stage, right? So in some sense, we never needed that distinction of stage and payload. So from my point of view, there's actually a lot of unknowns at the moment. We're just trying to rethink a little what we've done, because Linux is just so much more capable than it was, and the original motivations have changed. So I just wanted to try and think about, what should we be doing here? And learning about Surface just this morning was a surprise. Learning that they haven't used S3 for 3 or 4 years. So this is really a lot of open questions. It's a really good question. I don't know the answer.
But
Yeah.
they're running Windows, right? So I assume their kernel side looks a lot different than ours.
I don't see a reason Linux couldn't be fixed, but I don't think it will be for another 20 years. But I don't see a reason it couldn't be. So yeah, no, it's a good point. They get to fix all their drivers, and they've done a lot of really neat work fixing their drivers, and they're using the instruction for whatever it's called, something modern standby. Love the word modern. So modern standby comes with all this great stuff, but you got to rewrite you got to fix all your drivers. That's a big deal. But they were able to do it, and will Linux catch up? Don't know. So interesting question.
But so for the Coreboot stuff, would it maybe be easier to just configure the ACPI part or the PCI init part out of the RAM stage rather than dropping it completely? Because
yeah,
there were a lot of issues with just pulling the payload loading into the RAM stage.
You're right, and yeah, that might be the right way to go. But I think this is more about having a discussion and trying things out. So I think the Rampayload here, work that Subrata did, we learned a lot. I think Patrick Georgi's, so I want to revive his CL because I kind of want to revive the discussion. I learned something yesterday from the 3M Dev guys about their problems. So I think it's a good time just to reopen the discussion a little and see what the right path forward is. And clearly, in some situations, removing the RAM stage is just simply not an option. So we just need to maybe even sort of lay out the space in which it is an option, in which it isn't an option. But I think that I wasn't careful about explaining that idea last fall, and I think it's led to a lot of misunderstandings.
Okay,
So
thanks.
yeah.
Yeah, I have a little bit different view.
Mhm.
Do you customize the Linux kernel in the firmware?
No.
You don't?
No.
Okay. How you support a new bus?
I'm sorry?
New type of bus, like CXL, CCIX.
I would hope. I mean, the whole reason that Linux bus became practical in 1999 is we had self-describing buses. PCI was a big deal, right? No more dip switches, right? No more of this weird stuff. If you look in the SOCs in the last couple of years, we've sort of diverged away from self-describing buses, and in some places we're kind of going back to magic numbers, which is, I think, not a good development. So I would hope that any new thing like CXL, we would continue the goodness of PCI with the self-describing devices. If we fail to do that, we're creating a lot of problems.
And then ACPI table. I don't see how can you remove the ACPI table.
You put it in the initramfs. We did, Trammell did do that experiment, and when he told me what he was doing, I thought, you're nuts.
All the features,
Huh?
our management for Rust.
Yeah, I mean, sure, but if you generate it with IASL and then as part of your generation in initramfs, you drop it in a certain place, it gets loaded earlier. I've done this actually, so it gets loaded in the early going, and the kernel can't tell that it didn't come from the BIOS.
Then the last point is why you care about a server boot faster a few seconds.
Oh,
A server boot once or twice in a lifetime.
Not true.
Worry about.
Not true at all. In fact, we have cases which I can't talk too much about, but no, I can tell you the one story. You're AT&T. You have a server reboot. It takes too long to reboot. Just pick a server. It takes too long to reboot. Guess what you do next? You file paperwork with the FCC explaining why that took too long to reboot. That is a pain you do not want. So to my surprise, Tom Anschutz said, "Oh my God, if you can fix my boot time problem, you'll make me a very happy person." The next thing he said is, and by the way, I want everything running Linuxboot because I'm sick of waiting for all my routers and other things to boot. So yeah, no, 20 seconds or less is great.
The boot time is, if it's 2 lines, usually do the RAM testing, right? If you don't test,
not on the systems I've seen.
Yeah, but
I mean, it's actually from what we've seen, it's almost order n squared in the number of Dixies. It's horrible. So if you can take, for example, on this Tyan board, we were able to filter out of the 424 Dixies, all of which run, by the way, all of which seem to depend on each other, which means they all run at least twice. We filtered out 214 of those Dixies, and I didn't expect to notice the difference, and it was noticeably faster just to remove Dixies that you didn't even need. So no, it's not just RAM test. It's not by any means.
Customized. If I customize a regular UEFI BIOS, I can boot to Windows in 2 seconds.
Oh, great.
Right. So
why? So tell me why all my server nodes take 10 minutes.
It's a customization issue. It's not the boot process issue. That's what I think. Anything.
It's not our experience, but I can't argue if that's your experience.
Then my last point is, if manufacturer, they already test the UEFI boot to everything thoroughly, and then you throw in something that is never tested by the silicon vendor. I don't see what is the advantage.
I guess based on my experience with servers, I wouldn't want to say that things are tested.
Yeah, you need a test anyway. So
well, let's just say I would say that they're tested as thoroughly as we're testing them now with Linuxboot, because we can boot so quickly. I mean, if I boot in 20 seconds, I can do roughly 16 times as many tests a day as when you boot in 10 minutes. It becomes practical to do 1,000 test cycles. Not practical with UEFI off the shelf that I get from vendors, right? I mean, I've got a machine right now from a very credible company. God, it takes like 5 minutes before I can press the power button.
Wow, okay.
It's horrendous,
yeah,
right?
Yeah.
And then it's another 5 to 10 minutes before I have any kind of ability to interact with the machine. So, 20 seconds versus many minutes is a really big deal for testing. You cannot do a lot of testing if the machine takes 8 to 10 minutes to boot. You just can't. So
okay,
yeah.
Okay.
Hey Ron, how are you?
Hi.
Hey, so just to follow up with what Maurice was saying earlier, about some of the things that are platform dependent.
Yeah.
Like for example, if you take servers, we have PCI slots you have to bifurcate.
Yeah.
Based on how the number of slots are, number of width of the slots are, right?
Yeah.
And then you also have things like if you have PCI SSDs and hot plug, you have to know which slots are hot pluggable slots, what the addresses of those VPP ports. So a lot of things that are platform knowledge that comes along with it.
Yeah.
Not just you can ignore the platform and move everything to the Linux kernel. Right? Yeah. So that's I'm trying to understand how you're trying to solve that problem.
So so the hot plug thing, I pretty much don't buy, because there's like X million machines and data centers out there that nobody's ever going to hot plug anything, right? They roll them out and they run them.
Sorry, but PCI SSDs these days, you're right, never happened before. But with front panel PCI SSDs, if you have RAID configuration, and you can remove one and then you can replace it if it's a failing SSD. So it's happening now.
Yeah, so it depends on your on how you go about doing those things. But
I give
we should probably have a discussion offline because I don't know.
Okay.
This is being recorded.
Right. So again, but what I'm saying is it's just an example, right?
Yeah.
But a lot of platform specific things
Yeah.
that BIOS carries today.
If you want to make the case that this idea of putting the ACP tables in the initramfs is complete bunk, I'm not going to try and argue you out of it. Because you're probably right. It's just something that we did experiment with and found in some cases would actually work.
Okay.
Is it entirely practical? Not really sure. I note that on the RISC-V, one of the things on the Hi-5 or the FU540 chip is the mask ROM hands you an FDT, right? You get it right out of the mask ROM, you get an FDT, and you're supposed to build the rest. Funny story, the FDT we're getting seems to be complete garbage, so we're having to build it anyway in Linux. So, this argument can go either way. That's what we're learning. And I don't think there's any certainty as to the right way to do it.
And the second thing is just to add to this point on boot time. Right?
Mm-hmm.
So the majority of the boot time is taken by ECC init. So when you come up at a cold boot, memory is not initialized with zeros, which means the ECC doesn't match.
I know.
Right. So
I know that one very well. Yes.
So that's a major major time-consuming task
Mm-hmm.
to go and write all zeros so that ECC word matches with the data.
Hey, Ryan. Is most of our memory gone? And Ryan, is most of our boot time taken up with ECC init? No.
How big
it's
is
just
the
not. I mean, I'll give you an example. There, a lot of these things, there's some damn Pixie thing in there, which you got to turn off. And when Pixie goes to enumerate Ethernet, it'll wait 30 seconds on every Ethernet port to figure out that it doesn't have carrier.
Sure.
And Linux will do that step in seconds because it can turn them on all at once.
Yeah,
right?
for the boot
boot
selection, I agree with that, right?
Yeah. So but again, there are 424 Dixies in this one small server board, and they all time out on something.
Sure.
Okay. And I don't want them, and I don't need them, and I want to get rid of them. Sure. And when we do that, okay, typically our time goes from minutes to seconds. It just does. So, okay, maybe ECC init is important. I actually think there's better ways to do it than we're doing it today. But all that said, not what we're seeing. What we're seeing is a lot of badly written Dixies. We actually have one board, I won't name the vendor, but we found, it was an AMD board, and we found a bunch of Intel Dixies in there.
Sure.
So there's incredible sloppiness on the part of the companies shipping UEFI. Our proposal to solve the problem is to get rid of all that stuff, right?
Sure.
And when we do that, all of a sudden, gosh, our boot time is great.
Yeah. So
and further on the tie-in board where we hit, I'm sorry, the Winterfell board where we hit 20 seconds, the first thing we did actually was just replace the UEFI shell with the Linux kernel. Right. So that wasn't ECC init, right? Because that was a constant in each case.
Right. So basically, if you remember last OCP summit in Amsterdam, we demoed a 5-second warm reset and a 10-second cold reset on a OCP platform, server platform.
Yeah, it's great.
And again, we took a lot of things out of the Dixie phase.
Sure.
Things that you have platform dependency on, for example, BMC. But wait for BMC to come up, takes 20 seconds, right? And then you on a cold boot, so you have to wait for that. IPMI commands take a lot longer. So if you strip everything down to a bare minimum required, I can bring it down to 5 seconds and we demo it.
But I think you're supporting my argument.
So, but how do you...
We strip all that stuff out and it gets better.
Don't you need those stuff?
So ECC init is still occurring, but we strip all that stuff out and it got better.
Right, but then if you...
that's supporting, isn't that supporting my argument? Or
well,
not?
If you may take ECC init out,
then you crash. No, I'm not saying take ECC init out.
Okay.
I'm saying you demonstrated this really neat thing, 10-second boot, by stripping a lot of stuff out that you don't need. That's our whole argument.
I can demonstrate something that I can by taking away things I don't need for boot.
Yeah.
But I need for functionality. So if I need to have BMC logging all the errors that are coming up, I need the functionality. So if you start adding platform functionalities on top of your basic baseline, then you start adding boot time.
I don't need HTTPS Dixie. I don't need TCP IAP6 ping Dixie. I don't need sendmail Dixie, which we are finding. I don't need the sendmail Dixie password.
Right.
I don't need AHCI Dixie. I don't need ISA Dixie. I don't need VFAT Dixie. It's a long list, right? It's 214 things. I'm not going to do them all, right? And when I remove those things, it gets a lot faster.
Yeah.
ECC init is still occurring. So if I remove all these things, I'm down. I've chopped off 7 minutes and 40 seconds. It's not the ECC init. It's just not.
Sure. So those things that, like the HTTPS, those things, yeah, you are right. Those things.
And they always, by the way,
those things
not everybody knows this. Every single Dixie, at least it runs the init function, because there's the protocol GUID in the Dixie you cannot discover without running the init function.
Okay.
So all those Dixies run whether you think they run or not. They all run even if you think they're not configured. That was the shock for us, right? There's the file GUID and the protocol GUID, and you can't know the protocol GUID because it's not at a fixed place in the object. The only way you can learn a protocol GUID is run the init function in a Dixie. Every Dixie will run at least once. If any Dixie has dependencies on other Dixies, they'll run at least twice. And that's the problem. If you've got code from AMI that has a hidden dependency on a Dixie because the code's not written correctly, it'll run more than that. If you remove English.dxe because you don't know what English.dxe is, then the AMI firmware will crash.
Sure.
So, because it's not properly listed as a dependency in the AMI TSC.
Yeah.
So, nope, it's got to go. We want it all gone.
Thanks.
Yeah. But thank you. Those are good points. So, yeah.
Okay, thanks. That's it for questions, unfortunately. But yeah, let's have another round of applause. And